Welcome back. In this video, you'll learn about parametric derivatives. Let's get to it. Alright, so previously you've been introduced to parametric equations and how they can be used to represent plane curves. And so now we are ready to begin to use calculus with parametric equations in order to analyze those plane curves. And we're going to start with derivatives. And so remember that a derivative is the slope at a point on a function or along a curve. And so if you take a look at this plane curve right here, this plane curve would be represented by these two parametric equations. We have x equals f of t and y equals g of t. Both x and y are represented with functions of t, so for any value of t, you could plug them into these functions to get the corresponding x and y coordinate for a point along the plane curve. But let's say that we wanted to know the derivative, or the slope, at a specific point along that plane curve. How could we find that slope or that derivative? Well, assuming that the plane curve is smooth, it doesn't have any gaps or any holes, we could represent that plane curve with the rectangular equation y equals some function capital F of x. And so if we want to find the derivative of this plane curve, but parametrically, right, we want to look at parametric derivatives, what we can do is substitute what x and y are equal to into this equation so that it's in terms of t, and then take the derivative of that, right? Both y equals capital F of x and these two parametric equations both represent this plane curve, so we are allowed to make some substitutions here. We can replace y with g of t because y is equal to g of t, and we can replace this x with small f of t because x is equal to small f of t. And I say small f because this is a different function than this function right here, capital F. I'm just trying to make a distinction between those two functions. They are different, but if we make that substitution, we'll have g of t is equal to capital F of small f of t. All right, we just replaced y with g of t, that's what it's equal to, and x with small f of t, that's what that is equal to. And so now, if we take the derivative of both sides of the equation, what we'll have is g prime of t, that would be the derivative of g of t, and that will be equal to the derivative of capital F of small f of t. Now this function right here is a composite function, so in order to find the derivative, we're going to need to use the chain rule. So we would take the derivative of the outside function, which is capital F, and then multiply by the derivative of the inside function, which is small f of t. All right, so the derivative of the outside function will be capital F prime of that same inside function, small f of t, and that will be multiplied by the derivative of that inside function. So we're going to multiply by the derivative of small f of t, which will be small f prime of t. All right, and so now what we can do is substitute back x for small f of t in this capital F prime function. So what we'd have is g prime of t is equal to capital F prime of x times small f prime of t. And the reason we do that is because remember what we're trying to find here. We want to find the derivative of this plane curve. And so if we're looking at this original equation, capital F prime of x would be the derivative of that curve. And so that's what we have right here, capital F prime of x. And so we want to solve for that function, for that derivative. And so all we have to do to solve for that, to find that derivative, is divide both sides by small f prime of t, right? If we divide both sides by that derivative, small f prime of t, that will cancel out this one on this side of the equation, and we'll be left with g prime of t divided by small f prime of t, and that will be equal to capital F prime of x. The derivative of this function, or of this curve, capital F prime of x, is equal to g prime of t divided by f prime of t. The derivative of the function that represents y in terms of t divided by the derivative of the function that represents x in terms of t. And so another way that we could write this with a different notation, instead of f prime of x, we could use the y notation, which would be the derivative of y with respect to x. That would be equal to the derivative of y with respect to t, so we'd have dy dt, divided by the derivative of x with respect to t. And so we would have dx dt, right? So these two equations, or these two formulas, are the exact same thing. The derivative of the plane curve, or the parametric derivative, is equal to g prime of t divided by f prime of t, which is the derivative of y with respect to t divided by the derivative of x with respect to t, and that is dy dx. And so provided that the derivative of x with respect to t is not equal to 0, because you can't divide by 0, that would make this an undefined value, these two equations are the form of a parametric derivative. And this form right here is the one that I'm going to use for this video. Alright, and so to summarize, this is our formula for finding a parametric derivative. dy dx, the parametric derivative, will be equal to dy dt, the derivative of y with respect to t, divided by dx dt, which is the derivative of x with respect to t. And provided that that derivative is not equal to 0, this will represent the derivative of a set of parametric equations. And so, now that we know this formula, let's take a look at a couple examples of using it to find some parametric derivatives. Alright, so here's our first example. We want to find dy dx for the parametric equations. And so dy dx in this case is our parametric derivative that we want to find. And we have these two parametric equations that we want to find it for, x equals t squared and y equals t minus 1. And I have our formula here for us to reference. Dy dx is equal to dy dt divided by dx dt. And so the first thing that we want to do to find that parametric derivative, or dy dx, is to take the derivative of x and y with respect to t. So let's start with x. dx dt, the derivative of x with respect to t, will be equal to the derivative of t squared. And so if we use the power rule for derivatives on t squared, we'll multiply that 2 down and subtract 1 from the exponent. So we'll have 2 times t to the first power, right? Multiply 2 down and subtract 1 from 2. So we have a power of 1. But we don't typically write that first power. All right, and so that's dx dt. And then dy dt, the derivative of y with respect to t, will be equal to the derivative of t minus 1. Now the derivative of t, that's just going to be 1, because the derivative of a variable to the first power is just equal to its coefficient, which in this case would just be 1. We have 1t, and so that derivative is 1. And then the derivative of negative 1 is going to be 0, because negative 1 is a constant, and the derivative of all constants is 0. And so dy dt is just equal to 1. All right, and so now we have dx dt and dy dt, so now we can build dy dx, or find that parametric derivative for these parametric equations. And so we'll have dy dx is equal to dy dt, which is 1. So we'll have 1 divided by dx dt, which is 2t. So we'll divide by 2t. And that right there is the parametric derivative dy dx for this set of parametric equations. Let's take a look at another example. Alright, so here's our second example. Once again, we want to find dy dx for the parametric equations. In this case, we have x equals sine of t and y equals cosine of t. And so to find dy dx, we want to do the same thing we did in the previous example. You want to start by finding the derivative of x and y with respect to t. So we'll start by taking the derivative of x with respect to t. So dx dt is equal to the derivative of sine t. And the derivative of sine is cosine, so dx dt will be cosine t, and so that will be dx dt. And then dy dt, the derivative of y with respect to t, will be the derivative of cosine t. Now the derivative of cosine is negative sine, so dy dt will be negative sine t. Alright, so now we have dx dt and dy dt, so now we can find dy dx, our parametric derivative. So in this case, dy dx will be equal to dy dt, which is negative sine t, so we'll have negative sine t, divided by dx dt, which is cosine t, so we'll have cosine t. All right, now you could leave your answer in this form, but we can simplify it just a little bit. Remember one of your trig identities, that sine divided by cosine is equal to tangent, and so this is actually equal to negative tangent t, right? Sine divided by cosine is tangent, but that negative still needs to carry over, so we have negative tangent t as our parametric derivative for these parametric equations. And so that is the answer to this example. Negative tangent t is dy dx. Alright, so now you've seen how to find the first parametric derivative, but can we find the second derivative of parametric equations? Or can we find even higher order derivatives as well, such as the third derivative, the fourth derivative, and so on? How would we find those derivatives for a set of parametric equations? Well, in order to find those higher order derivatives, we first need to start with our first derivative, right? dy dx is equal to dy dt divided by dx dt. And what we want to do is take a derivative of this first derivative with respect to x. Now that might seem a little off at first. You would probably expect that we would derive with respect to t, but remember that x in your parametric equation is defined with t, and so we are allowed to take the derivative of both sides of this equation with respect to x. All right, and so if we do that, we'll have the derivative with respect to x of dy dx, and that will be equal to the derivative with respect to x of dy dt divided by dx dt. All right, now the reason we take the derivative with respect to x is so that this first derivative, dy dx, can become the second derivative, which has this notation. We have d squared y divided by dx squared. Hopefully you remember this notation from way back earlier in calculus when we first looked at higher order derivatives. This represents the second derivative, and this is going to be equal to the derivative with respect to x of dy dt divided by dx dt. All right, now what we're going to do here is find a formula for the second derivative by simplifying what we have over here just a little bit. And the first thing we're going to do is multiply by a form of 1 divided by dt. Now this might seem a little abstract at first, but this is going to help us simplify what we have on this side of the equation. You're always allowed to multiply by a form of 1 because multiplying by 1 doesn't change anything in your equation. All right, 1 divided by dt divided by itself is just 1, so we're just multiplying by 1 here. And so what we're going to do is multiply this into d divided by dx. So what we're going to have is d times 1 divided by dt, so we're going to have d dt divided by dx times 1 divided by dt, which will be dx dt. And that's going to be multiplied by dy dt divided by dx dt. So we'll have dy dt divided by dx dt. All right, now at this point it looks like we just made things more complicated, but we can actually multiply by another form of 1 that is really going to help simplify things into a nice formula that we can use to find the second derivative. What we want to do now is multiply by a form of 1 of the reciprocal of dx dt. Notice that we have two of them in the denominator here. We have dx dt times dx dt. If we multiply by a form of 1 of the reciprocal of that, which means we're flipping the numerator and denominator, so we'll have dt dx divided by dt dx. What's going to happen is this dx will cancel out with that dx, this dt will cancel out with this dt, and this dt will cancel out with this dt. Right? So we are allowed to do this because dt divided by dx divided by itself is just a form of 1. We're only multiplying by 1 again, so we're not really changing the value of this second derivative. We're just changing its form, how it looks. And so if we simplify, we will have that the second derivative is equal to d dt times dy dx. Right? After that cancellation, we're left with dy in the numerator and dx in the denominator, and then this is divided by dx dt, right? That's all that's left in the denominator. This dx dt and this dt dx cancel each other out, so we only have dx dt in that denominator. And so now what we're left with is the formula that we can use to find the second derivative. It looks a little weird at first, but if I rewrite this multiplication sign to be in this form, or this notation, now it maybe makes a little bit more sense. We have ddt, or the derivative with respect to t, of dy dx. dy dx is our first derivative, and that will be in terms of t, dy dt divided by dx dt. So we will take the derivative of the first derivative with respect to t and divide that by dx dt, the same thing that we divided by in the first derivative. And so the second derivative calculation isn't all too bad. You just have to take the derivative of your first derivative with respect to t and divide by dx dt. All right, and then if we wanted to find more derivatives, we wanted to find more higher order derivatives, like the third derivative or the fourth derivative and so on, all you would have to do is replace what you're taking the derivative of with respect to t in that numerator with the previous derivative. So the third derivative would be equal to d dt of the second derivative, the derivative with respect to t of the second derivative, divided by dx dt. And then the fourth derivative would be the derivative with respect to t of the third derivative, divided by dx dt. And so you can kind of see the pattern here. Higher order derivatives for parametric equations just involves taking the previous derivative, differentiating it with respect to t, and then dividing by dx dt. And so to summarize, here are the formulas for the second and third parametric derivatives, but of course you could also find the fourth, fifth, sixth, and so on by just following the same pattern that you can see with these two formulas. The second derivative is equal to the derivative with respect to t of the first derivative, dy dx, and that's divided by dx dt. And the third derivative is equal to the derivative with respect to t of the second derivative divided by dx dt. Okay? And so now that we have these formulas for finding higher order parametric derivatives, let's look at an example of finding some higher order parametric derivatives. All right, so here's our example. We want to find the second derivative and the third derivative for the parametric equations. So we have x equals t squared minus 2 and y equals 2 times t cubed. All right, so now in order to find the second and third derivatives, we do need to know the first derivative. Right, I have our formula here for the second derivative. The second derivative is equal to d dt of dy dx divided by dx dt. So we need to know that first derivative in order to find the second derivative. And then in the same way, we're going to need that second derivative to find the third derivative. All right, so we're going to go through this problem derivative by derivative. And so let's start by just finding that first derivative, dy dx. And in order to do that, we need to find the derivative of x and y with respect to t. And so let's start with x. dx dt will be equal to the derivative of t squared minus 2. If we take the derivative of t squared, we need to use the power rule for derivatives. We'll multiply the exponent down and subtract 1 from the exponent. So we'll have 2t to the first power. And then the derivative of negative 2 is 0 because the negative 2 is a constant and the derivative of all constants is 0. All right, and so that's dx dt. And then dy dt will be equal to the derivative of 2t cubed. Once again, we want to use the power rule for derivatives here. We'll multiply that exponent down. So 2 times 3 is 6. So we'll have 6 times t to the power of 3 minus 1. And that will be 2. So we have 6t squared as our derivative, dy dt. Okay, so now we can build our first derivative, which is dy dx, and that is equal to dy dt divided by dx dt. So we're going to have 6t squared, that's dy dt, divided by 2t, which is dx dt. All right, and so that's our first derivative, but before we use it to find the second derivative, we can actually simplify this a little bit. 6 divided by 2 is 3, and t squared divided by t is just t, right? So this would be equal to 3t. 6 divided by 2 is 3, and this t will cancel out with one of those t's. And so, now that we have our first derivative in its simplest form, let's use it to find our second derivative. The second derivative, d squared y divided by dx squared, is equal to d dt, or the derivative with respect to t, of that first derivative that we just found, which is 3t. So we'll take the derivative with respect to t of 3t, and that's going to be divided by dx dt, which we found earlier, is still 2t. So we'll have 2t. All right, and so now if we take the derivative of 3t with respect to t, that's just going to be 3, right? The derivative of t to the first power is just going to be equal to the coefficient. So this will be equal to 3 divided by 2t. And so 3 divided by 2t is the second derivative of these parametric equations. And so that's one of the answers we needed to find. We found our second derivative, but now we want to find our third derivative. And that's going to involve that second derivative that we just found. We're practically going to use this same formula, but instead of taking the derivative with respect to t of the first derivative, we're going to take the derivative with respect to t of the second derivative. And we're still going to divide by dx dt. So the third derivative, d cubed y divided by dx cubed, will be equal to the derivative with respect to t of that second derivative, but now I'm going to rewrite it a little bit just to make it easier to find the derivative of it. We can move t to the numerator by making the exponent negative. So this second derivative would also be equal to 3/2 times t to the power of negative 1, right? This is t to the first power, but if we move it to the numerator, or just move it out of the denominator, that power is going to become negative, but now we can more easily see how to take its derivative with the power rule. That's going to make our derivative process a lot easier. And so we'll have 3 halves times t to the negative first power. That's our second derivative that we want to take the derivative of with respect to t. And then we're still going to be dividing by that same denominator of dx dt, which is still 2t. So we'll have 2t in the denominator. All right, and so now if we simplify, this will be equal to the derivative with respect to t of this second derivative. We'll multiply that exponent down and subtract 1 from the exponent. So we'll have negative 3 halves times t to the power of negative 2 divided by 2t, right? Negative 1 times 3 halves is negative 3 halves. Subtract 1 from negative 1, and we have negative 2. Okay, so now we just have to simplify this into its simplest form, and then we will have the third derivative of these parametric equations. So if I clean up my work a little bit, let's simplify our third derivative by first moving this fraction out to the front and then moving t to the power of negative 2 to the denominator so that that exponent is positive. So this will be equal to negative 3 halves times 1 divided by 2t times t squared. Right, moving t to the power of negative 2 to the denominator makes that power positive, so we have t to the power of positive 2, or just t squared. Now if we simplify, we can multiply negative 3 into that numerator, and multiply 2 by 2 to get 4, and t times t squared is t cubed. So this is equal to negative 3 divided by 4t cubed. And that right there is the third derivative for these parametric equations. All right, and so now we have completed this example. We found the second derivative right here, 3 divided by 2t, and we found the third derivative, negative 3 divided by 4t cubed. Okay, and so with that, this was the last example for this video on finding parametric derivatives. If you want to see some more examples of finding parametric derivatives, whether that be the first derivative, second derivative, or third derivative, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. And so if you have any questions, leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.